This is a guide to doing lab 1. You are given a second order dynamical system described by this second order differential equation. The input to the system is f of t, the output is x of t, and the constants zeta and omega n are specified here. The derivatives of x are x dot and x double dot. For part A, you're supposed to use ODE43 to simulate this system and produce x from time 0 through 5 with input equal to 0 and these initial conditions for x. So to do this, you need to convert this second order differential equation into a set of two first order differential equations by making use of state variables. So we can define one state variable to be the position x. So x1 is x and the second state variable x2 is the velocity x dot. So using them in there, we get the following two differential equations. X2 is x1 dot and this. We can get it into a better notation by using vectors to represent the state variables. So we combine x1 and x2 into a vector x, which is a lowercase bold x, and the derivatives of the state variables x1 dot and x2 dot are combined together in the vector x dot. So bold lowercase x dot is the derivative of the bold lowercase x. Now we can rearrange these two equations in terms to get the derivatives in terms of the state variables. So we can write x1 dot as x2 plus 0 times x1 plus 0 times f. x2 dot is this, and once we've done that, we can write it in a matrix form. So the derivatives x1 dot and x2 dot on this side is this matrix times the state variables x1 and x2, and this matrix times f. And using then the symbols for these matrices, we get bold lowercase x dot is equal to bold uppercase A, which is this matrix, times the bold lowercase x, the original state vector, plus b times f, where b is this matrix and f is the input. Now we have to implement this in MATLAB and have MATLAB simulate this for the given time and initial condition. So first of all, we close all figure windows, we clear the memory of existing variables, we clear the command window, and I've put in a comment that makes it clear to the user that the state variable x has two components, x1 and x2. x1 is the position x and x2 is the velocity x dot. To implement the differential equation, ODE23 requires you to define a function, and that function accepts a time t and a value of x, and it is supposed to calculate the derivative of x at that time and return that value. So given t and x, this function will return x dot based on the equations defined for this particular problem. So the derivative x dot was defined like this. This x, it could be a single scalar variable, in which case the derivative would also be a single scalar variable. It could also be a vector, like a state vector consisting of multiple state variables, in which case the derivative would also be a vector. So this is the latter case. X is our state vector, and we'll use this equation to compute the derivative. So here it is. The derivative of x is a times x plus b times u, where the matrix A is defined like this using the constants given in the problem. Matrix B is this, and in part A we were told that the input to the system is 0. So when we execute this program, okay, and ODE23, the first argument is a handle to the function that implements the derivative. So this is the function that is implementing the derivative of x. You prepend this @ sign, and then you specify the time for which you will run the simulation. I'll run it for 0 to 5 seconds, and the initial conditions x naught. So this is the initial condition for the first state variable for x, and this is the initial velocity. So ODE23 will start at time 0, and it uses a predefined built-in increment to increment time up till time 5. At time 0 it will use these initial conditions, and it will keep on computing x at each one of those instants. And it will return the vector t, which will have all those time values, and a vector x, which will have the values of x that it finds out. When you now x is not a scalar in this case, x is a vector which will have uh, two columns. That's how it stores the results. When you give the plot command, it will have the time on the x-axis, and since x was made up of two columns, you will see two separate plots on the same figure. And then I've labeled the x-axis as time and the y-axis as the state variables, and you can color code the two plots using the legend function, so it will automatically label the first plot as the distance and the second plot as the speed. Or you could have written x1 and x2, and then I've given a title for the plot. When you run this, so you get something like this. You have the first state variable, which is the distance, and the second state variable, which is the speed. And we can see that the position is starting at point 4, which was our initial condition. And the system is kind of like a mass connected to a spring. So you have some initial displacement, you stretch the spring a little bit, then you release it at time 0, and your mass, it moves back to the resting state 0. And for this case, there is so much damping that you do not see any oscillations. It just slowly descends to 0. And as it moves, you see the velocity shooting down to a peak value, a negative value, because it's pulling it. And then as it approaches its resting state, the velocity also decays to 0. So it looks like it's correct. For the second part, you it's pretty much the same, except for you have a new set of initial conditions, both 0, and the input is also not 0. The input is defined somewhat like this. So the only difference would be here in the where you are implementing the derivative. Your u is not 0 anymore. Your u is 1 for time less than 2, and it's 0 otherwise, and the rest of the function is same. In your main program, you've been given a new set of initial conditions, and I'm just going to run this. Oh, you get something like this. So you applied some force on your mass for 2 seconds, so you ended up pulling it to a certain distance, and then after some time you couldn't pull it anymore. It started to flatten out, and once you released it, it went back to its resting state. So this was how you were supposed to do this part. There is another way to approach part B. You can break your simulation into two segments. A segment going from time 0 to time 2 with the given initial conditions. You simulate it, that's fine. And in the implementation, you can just hard code u as 1 because you are only running this function for that 1 second. And then for times 2 through 5, you would have so this would be something different. It would be a function where u is 1, and you would also have to write a new function where u is 0. Here the simulation time is from 2 to 5, and you have to make sure your initial conditions in this case are the final conditions of the previous case. So this simulation ended with the state vector in this condition. So the last row of x, that's your x1 and x2, the final value of x1 and x2 from this simulation. So these have to be the initial conditions for the second simulation. And you can do it like that, but you should get something like this. So this is problem 1. In problem 2, assuming 0 initial conditions, you were asked to take the Laplace transform. Here it is. So no derivative terms or the initial condition term. This is the simple Laplace transform. In part B, uh, find the transfer function. So the transfer function is defined as the output over the input, the output being x in Laplace domain x of s, the input being f of s, and if you move things around you get this. So this is your transfer function. To implement it using the TF function, you need to find out the numerator coefficient. So we just have one numerator coefficient 1. So my numerator coefficient array is just 1. The denominator coefficients are 1, whatever that is and whatever that is. I think this is 16 and this is 64. So your denominator vector is 1, 32, 64. So it was 32. And then you use the TF function, numerator denominator, which gives you the system transfer function. And then to get the step response for problem 2C, you just use the step function specifying a final time, the stopping time for your step response. In 2D, you were asked to use f, uh, a sinusoidal wave of amplitude 1.2 and a frequency of 0.75 Hz. So you set A to 1.2, frequency to 0.75 Hz, and your signal will be A sine 2 pi ft. The t is the time, and the time increments are decided by you. So I've chosen uh, like a sampling rate of 20 times the frequency. So the higher the sampling rate, the smoother the curves look. So this works fine. And then you use the LSIM function. LSIM, the transfer function, the input, which is f, and the time that you will run the simulation for. And when you run this, so this is what the step response looks like. You applied a constant force on the spring starting at time 0, and the mass moved, and after some time this it just flattened out. When you apply the sinusoid, it doesn't move much, but it does. If you zoom in, you should be able to see that the position does move. So that's your problem 2. Problem